if you'll need, so if you don't know, the answer is no. You should say BMI in English. If you don't know, the answer is no. Right? Enjoy.
Hi everybody, thank you to be here today. We are UPS in Space, the astronomy club of UT3. Since 2009 we were created. Our goal is to popularize astronomy. We have people from L1 to thesis. Actually, we are 74 for now. Our activities are general public lectures, like today, and our next one will be on January 21st. It will be about Hayabusa 2. It's an asteroid sample return. We have also animations for general public, solar and night observation. Next observation will be with the meteor 1 night per month or 1 per week. For our members, we visit to scientific facilities like Divinity Observatories, Jolimo Observatory, the IRAP, Institute of Astrophysics. We also have internal activities like yesterday. And our permanences are every Tuesday. We have also a future astronomical observatory. It will be on future building, the house of students and staff near building U4. The opening will be on the reactor 2021-2022. And on the roof we will be have a dome for our observatory. It will be a 4-meter diameter. Our instrumentation, it will be for scientific applications like asteroid, comet, exoplanet, and many more. The destination is for students like you, and also for high school students for scientific mediation. We have a lot of supports, like Minister, Director General of the Cité d'Espace, President of University, Mayor of Toulouse, and many more. We have some partners like the university and some observatories, and a lot of supports, institutional and associations. We have a bank partnership for members and our shop with clothes, goodies, and many more. You can follow us on our website and on every social media. And the board. Thank you.
Hello to everyone. Thank you very much for coming along. As you can probably hear already by my accent, I'm actually British. So if any of the English is causing you any trouble, please don't hesitate to raise your hand and say either I'm speaking too quickly. This is not the first time I've heard that. Even British people tell me that. So yeah, please don't hesitate to stop me or ask me specifically if there's something you don't understand. So I've been asked to talk about black holes, so I'm going to talk a little bit about why black holes should exist, And also, I think more importantly, how we can go about observing them. How can we find the black holes that are supposed to be out there in the universe somewhere? So the outline of the talk is, as you can see here, I'm just going to talk a very little bit about the first people to propose black holes. So you're probably thinking I'm going to say Einstein, but that's not the first person I'm going to talk about. But I will talk about relativity. I'm not going to show you any equations concerning relativity, and I'm not going to try and derive anything either. But I will give you some hand-waving description of relativity and its consequences, because one of the consequences of relativity is black holes. So then I'm going to talk a little bit about the different types of black holes that we can expect, and those which are real astrophysical black holes. Then, as I said, I'll talk about how to detect these black holes, and that's probably more where my speciality lies. I'll also talk about some of the properties of black holes. There are not many properties of black holes, but what we do know about them. And also why we want to study them. There are a number of different questions that are open still around black holes, and I'm going to mention some of these questions and give you some hints about how we hope to answer these kinds of questions in the future. So, who proposed the black hole first? Well, as you can see here, the first person to actually propose the concept of a black hole was John Mitchell, and this was 236 years ago. So this is not a new subject, but it did take a long time for it to develop. So John Mitchell proposed, after studying stars, that you could possibly have such a massive star that's got such a strong gravitational field that not even light could escape from that gravitational field, which would make the star dark. There would be no light coming from that star, and that's why he called these stars dark stars, and this name remained for another couple of hundred years actually. Not long after, actually 16 years afterwards, and apparently independently according to historians, Pierre-Simon Laplace also proposed that such a dark star could exist. He deduced a slightly different mass to John Mitchell, but he went a little bit further, and 3 years later, in 1799, he actually gave a mathematical description of this dark star that could exist. However, we had to wait more than 100 years for things to develop. And this is primarily due to Albert Einstein, you can see from 1879 to 1955. So Einstein was fascinated by most of the physical world. He proposed many different theories, many of these have been validated. In his quest to try and understand the physical universe, he developed special relativity in 1905. And special relativity, again, I'm not going to give you any equations, but it describes the fact that all the laws of physics are the same in an inertial frame. What's an inertial frame? It's a frame where there's no forces that are really exerting on the frame to accelerate it, etc. And he also said that the speed of light in a vacuum was a constant. So this is 3 times 10 to the 8 meters per second. And I'm going to come back to that value during this talk. So that was his first attempt at trying to explain the universe. And then he generalized his theory with a general theory of relativity in 1915. So you could probably think about general relativity as an extension of what Newton proposed more than 200 years before that. So as you know, Newton was fascinated by gravity, why we should stay on the Earth and not float off into space, for example. And there's this very famous story that apparently he was sitting under an apple tree and the apple fell onto his head. And he suddenly realized that gravity must be something to do with attraction, to do with the mass of the Earth. So this remains, this is true. Newton's gravity still holds in many of the general situations, but once we go to very extreme situations, we can no longer just use Newton's gravity. We need to move into something a little bit more complex. And that is what Einstein proposed with his general relativity. So yeah, let's just like you to think of this as Newton's theory of relativity, but with some added extras. So it's still the mass that causes the gravity, but not for the same reasons as Newton described. To try and understand general relativity, which is not very clear, and I can see that this figure is also not particularly clear on the slides. I want you to think of the universe as we can see it here. Hopefully at least the people in the front can see there are some lines drawn on this. And this is like some kind of mattress, maybe you could imagine it, a mattress such as you have on your bed. And if you place a mass on a mattress, so a weight, maybe, I don't know, a cricket ball, for instance, on your mattress, it's going to slightly deform the mattress, but only a tiny, tiny little bit. However, if you come along and put a bowling ball onto the mattress, you're going to see it's going to deform it more. There's going to be some kind of like dip in the mattress. And that's what the masses do in what we call space-time, and that's the 4 coordinates we need to describe the universe according to general relativity. So it's not too difficult to understand the 4 coordinates we've got. X, Y, and Z, you're used to it. They're the 3 dimensions, so X, Y, and Z, that you're used to seeing. You see the world in 3 dimensions. But what's proposed here is you need a 4th dimension to fully understand space, and that's what's called space-time, because the 4th dimension is time, and it's totally linked to the X and Y and the Z dimension. Okay? And that's what this is trying to represent, this artist's view of what the space-time looks like. As I say, try and imagine it's like some kind of mattress. So for those of you who can see clear enough, you can see there's some lines here that have been deformed by the masses that have been placed upon here. So this is the small mass, this is Earth, and there's a small deformation of space-time. And you can see the lines are slightly, they're no longer straight, they're slightly curved around this mass here. And then we can place a bigger mass, the sun, for instance, on this mattress, and you can see that the lines are further deformed. They're quite curved around the bigger mass, the sun. And this is what causes, for instance, the gravity that you experience. That's to say, if you've got some kind of body coming towards your mass that's here, the body is coming towards it, it's going to be forced to follow these curved lines around your object. Okay? And so you would enter, for instance, an object coming from here could enter orbit around your mass, around the sun, for instance. Or also light, the path will be deviated of light that's passing close to the sun. So that was all very good. In 1915 he proposed his theory of relativity, but not so many people were interested. Why should they be interested? What did it really mean to them? Well, there's many, many different predictions of general relativity, and one of those is the fact that we've just mentioned, that if you have light that comes close to the sun, for instance, which is a large mass, it's going to be deviated. So if you have a star that was here, the light would be bent around the sun, and so a star that was behind the sun could actually be seen on Earth because of the effects of general relativity. So that seems great. How are you going to verify that? I mean, you can't detect the light from a star behind the sun because it's drowned out by the light of the sun itself. However, as luck would have it, on the 29th of May 1919, there was a solar eclipse. So what happens in a solar eclipse? The Earth is here, and it has the moon that's orbiting around the Earth, and the moon places itself between the Earth and the sun, thus blocking out the light from the sun. This particular eclipse was very interesting for 2 reasons. It was quite a long eclipse, but also during this eclipse there was supposed to be a stellar cluster called the Hyades that was supposed to be right directly behind the sun. So it was predicted from relativity that the light from this cluster of stars should be visible as the sun was eclipsed by the moon passing in front of the Earth. And that's exactly what we're seeing. And so it was the first validation that relativity seemed to hold up as a very good law of gravity. And so you can understand from that the path of the light is deviated by this mass. So that's cool. We've seen that the sun can deviate the light. But we can get something that's got a much greater gravitational potential, something that's got a much stronger gravitational force, if you prefer. This is a normal star. In fact, it doesn't look like our sun. This star is blue. And the reason the star is blue is because it's a particularly massive star. That means it probably weighs maybe 50, 100, or possibly 200 times the mass of our sun. So our sun is 2 times 10 to the 30 kilograms, okay? And this is maybe 100 or 200 times more massive, so it's pretty good. And stars, all stars that we know that shine like our sun, or maybe this blue star in this image, shine because there's fusion of hydrogen in its core. What does that mean? It means that 4 hydrogen atoms get close enough together, they're heated on the inside of the star, and they can then, under the pressure, form a single atom of helium. This might seem unimportant, but actually as the 4 atoms of hydrogen are fused together to create an atom of helium, it also releases some energy. And it was actually Einstein that realized that's how stars can shine for so long. This has been a big open problem for a very long time that no one could understand how a star can shine for millions or billions even of years. So that's good. We got a star and it's in equilibrium. It stays as it is because fusion is going on in its core. That's great. We fuse the hydrogen to create helium, but at some point we're going to find ourselves short of hydrogen. There's not going to be some hydrogen to carry on fusing to create helium, and that's going to cause us a problem. So if we stop fusing the hydrogen to create helium because we don't have enough hydrogen there to do so, the forces that were pushing outwards, thanks to this fusion, this radiative pressure that was on the inside, that was balancing the gravitational force of the star that pushes inwards, so because of the mass of the star, this outward force is going to disappear, and you're still only going to have the gravitational force from the star that's going to push down on the star and make it smaller and smaller. As luck would have it, as this is such a massive star, it's so massive that during this process we can get to such high temperatures and high pressures on the inside that actually we can start to fuse the helium to create carbon. So that's good. We re-establish an equilibrium and the star continues to shine until we get to the point where there's not enough helium to carry on fusing to create carbon, and we go through the same process again. Our star will begin to collapse, and then we can start to fuse carbon to produce higher, more heavier elements such as oxygen, nitrogen, etc. The same process will repeat several times until we reach, in the center of this star, a core of iron. It's not energetically favorable to fuse the iron to create something else, and so we don't have this pressure pushing outwards, and only the gravitational pressure of this star, and so the whole star is going to collapse at the end of its life. And it's going to collapse until it gets smaller and smaller and smaller and smaller and more dense, until what we call, it becomes a singularity. Or, as you may know it, otherwise known, a black hole. And this is how we believe that stellar mass black holes are formed. They're called stellar mass because they're formed from stars. There are other types of black holes, and we'll talk about those in a few moments. So we can have black holes, these singularities in space. They're extremely dense because they've got very small radii, but they've got huge masses. They can have masses of maybe 10, 20 times the mass of our sun. Some of the material is lost during this evolution from the star to the black hole. Just to note that although we use black hole all the time now, I spoke about dark stars in the beginning. Black holes was actually, the term was actually coined back in 1967. So until that time, these things were talked about as dark stars. And in fact, John Wheeler was giving a talk about these dark stars, and some person in the audience of the talk decided to use the term black hole. And ever since that time, we've used the term black hole, but actually nobody knows who it was in the audience that used this term. So we've now got a very, very strong gravitational field thanks to this very dense, compact star. And these black holes, as we can see them here, represented by the artist's view, are a result of general relativity. So So if we take the Einstein's equations, which I have not taken here because they look horrific and they're very difficult to solve, if we took the Einstein's equations, we can find that there are actually 4 solutions to Einstein's equations. During this collapse from our star to a black hole, all of the parameters of the star, all the complicated physics and stuff of the star are actually washed out. And in fact, a black hole is described by only 3 parameters, and that's what we call the no-hair theorem. So the 3 parameters are the mass, how much the black hole weighs, the electric charge, so if it's positive or if it's negative, and how positive and how negative it is, and what we call the angular momentum, or if you prefer to think of that, the rotation of the black hole. Okay. So you can imagine black holes that are rotating like the sun, like the earth, like the moon, like all the other stars that you see. Or you can also have a solution where your black hole does not rotate. Okay? This is the angular momentum. So, as I say, there are 4 solutions of Einstein's equations, and it's not Einstein that found the solutions. He said that this is going to be very difficult to resolve, and he didn't do this. And a number of different people did work on this, and they did find the 4 solutions. Some very rapidly. The first one was straight after the theory of relativity was proposed, and this is what's called the Schwarzschild solution. And this is the simplest kind of black hole. I've already told you a black hole has only got 3 parameters, and I'm going to come back to the electric charge in a few moments. But the Schwarzschild solution actually only depends on the mass of the black hole, and that's it. So it's extremely simple to understand, and we'll look at this kind of black hole in a few moments. So it's not a rotating black hole, it's just static, it's just sat there, and it's just got mass. Then there's the Reisner-Nordström solution, put together by Reisner in 1916 and Nordström in 1918. And this black hole depends on mass, but also on the electric charge. Later on, in 1963, Roy Kerr put together the Kerr solution, and this is for rotating black holes. This is more complex, and we'll look at some rotating black holes in a few minutes, and there's some added complexity that we'll have to add in there to try and understand our rotating black hole. So this black hole has got mass, and I just said it's rotating, so it's got angular momentum, but there's no charge. And then there's the 4th solution, put together by both Kerr and Newman. And this has got all 3 parameters. So we've got the mass, the electric charge, and the angular momentum. However, you can imagine if we create a black hole in the universe, it doesn't happen in a bubble, it's not all on its own, there's other things around. We've just had a star that's gone through some kind of collapse, there's material absolutely everywhere. So if you create a black hole with electric charge, imagine your black hole is positively charged. There's material all around, charged material, neutral material, and if you've got a positive black hole, the negatively charged ions that are close by will be attracted towards your black hole and neutralize it. So we don't believe that astrophysical black holes can have a charge. There's no reason why it should be able to retain a charge. And so the only 2 types of black hole we expect in an astrophysical scenario are these 2. The Schwarzschild solution, static black hole that depends only on mass, and the Kerr solution, where you've got a black hole which has got angular momentum, so it's got rotation. So we need to understand a little bit about our objects. Are black holes static? Or maybe they're all rotating? Or maybe they're rotating at a maximum rate, or maybe they're just rotating a tiny little bit? We don't know. We'd like to know. That's something we'd like to understand. And the theory of relativity doesn't give us this information. So we need to observe these black holes and find out. So there's some parameters that we can determine thanks to the mass and also thanks to the rotation of our black hole. And the first one I'm going to talk about is the event horizon. So what is the event horizon and why does it happen? This is just a regular star like our sun. So we'll go back to the situation we had during the eclipse, for instance. And we know that the light can approach the sun, it's deviated, we saw that during the eclipse, but it will go around the sun and then we can detect it. Okay? However, the black hole has got such a strong gravitational field, it deforms so much the space-time that as light approaches a special radius, which is what we call the event horizon, as it reaches this radius, the curvature of space-time, you can see as it drops into the black hole, is so strong that not even something with a velocity of 3 times 10 to the meters per second can push its way out of that gravitational potential. So at this radius, not even light can escape this black hole. And that's what we call the event horizon, and that is why we talk about black holes being black, because there's no light that can get past here. We can see light from just outside, but we can't see the light from the inside. So our star appears black. It's a star, but we can't see it by traditional methods. And I'll talk about the methods we can use to find it in a little while. So this is called the event horizon, and where the event horizon is actually depends on the type of black hole, whether it's a Schwarzschild black hole, so one that's not rotating, or one that is rotating, and it depends on how much. So in this first diagram here, on the left, you can see an artist's impression of a Schwarzschild black hole. The black hole is this object here in the middle, and around it we can see a certain amount of material. Where this material comes from, we'll talk about that as well in a few moments. But there's often gas and dust around a black hole. As I said, it's just been formed from a massive star, so there's stuff all around. So we've got our Schwarzschild black hole. Its spin, its rotation, is 0. Okay, it's not rotating. We've just said that. And then we've got our curved black hole, and it can have a spin, this A star here, which can reach a maximum value of 1. Okay, so it's greater than 0 with a maximum value of 1. We can also have negative values, and we're going to come on to those in a few minutes. So we can calculate the radius of our black hole using this formula. So we've just got 1 plus 1 minus A star squared, and the square root of all of this bracket here, times G, which is the gravitational constant, M, the mass of our object, which we've said it depends on the mass, and c squared, which is just the speed of light in the vacuum, which we discussed earlier. That looks complicated, but actually it's very simple, because here we've got a 0. So we stick a 0 in here, and we just get 2gm over c squared. So the radius, this event horizon we just discussed, for our static black hole is just 2 times the gravitational constant times the mass of the black hole divided by speed of light in the vacuum squared. So it's not complicated. I said black holes are simple. There's only 3 parameters. If we consider the maximum spin, so A is just 1, then we can determine as well, if we stick 1 in here, this term cancels, and therefore we've just got our event horizon that is gm over c squared. So if we can measure the light to where the light gets to around our black hole, we can work out whether it's static, or if it's getting closer in, it's a rotating black hole. Okay? So this is almost the same image, but not quite. That was the light. But we talked about this material. We've got like gas and dust that's forming this disk all around. And actually the material can't get as close. Matter can't get up to the same speeds as light, and therefore it's going to be perturbed by the gravitational potential before it gets to this last radius, this event horizon. And where this material can get to, okay, it can keep circulating the black hole up to a certain radius, which is called the innermost stable circular orbit, which is an absolute nightmare to say, especially if you had a couple of drinks. And therefore we call it the ISCO. And so I will refer to this as the ISCO from now on. So the ISCO, we can calculate it for our Schwarzschild black hole, the one that's not spinning, and it's about 6 times gm over c squared. So it's 3 times the event horizon for the static black hole. But the ISCO can go all the way in for a maximally rotating black hole, all the way in to the event horizon for a rotating black hole. So you can see, if we can measure the matter that's around it, we've also got some other idea about whether or not it's a spinning black hole or if it's a static black hole. Because this one is getting nowhere near the black hole, whereas this one's getting very close. So why does this happen? Why is there a difference between the spinning black hole and the static black hole? This is due to something we call frame dragging. So this is the curved black hole, and what happens in the curved black hole, the spinning black hole, is that actually the whole of space-time gets dragged along with the black hole. So we've got a rotating black hole, and it drags the space-time, these 4 dimensions, x, y, z, and t, in with it. And that's what we try to represent with these spirals that get closer and closer and turn more quickly around the black hole as it gets closer to the black hole, which is found in the center of here. If this was a Schwarzschild black hole, these lines would just be simply radial lines extending outwards from the black hole. So the material is getting dragged in towards the black hole as you get a more and more spinning black hole, these curved black holes. So if we imagine a particle that's really, really far away from our black hole, that's not spinning at all, it's just there, and as it gets closer and closer to the black hole, even if it's not spinning, it's going to start to spin with our spinning black hole in the direction of the black hole. So this is the black hole, the black dot, and that's the direction of the spin. And we can see our particle starts to spin in the same direction. But now we can imagine another particle. We can imagine a particle that's actually got a spin in an opposite sense. It's rotating in the other way to the black hole. So the particle's coming in like this, and our black hole is going the other way round. The particle's going to keep going around for a certain time until it gets closer to the black hole, and then the black hole frame dragging is going to be so important, it's actually going to change the direction of that particle and then drag it in the same direction as our black hole. So we can go back to this plot and we can add another one in now. So the one we were looking at before, this is the one with no spin. We can see the black hole and our material doesn't get so close where it's 6 gm/c². This is when we've got the material that's rotating maximally, so A equals 1, and it gets very close to the black hole. But if we've got the material that's going in the opposite direction, so now we've got the black hole going in this direction and the material going this way, we see that actually the material is even further out. So we can measure the spin, whether it's in, this is called prograde because it's in the same direction as the black hole, and this one's called retrograde because it's in the opposite direction to the black hole. And we can measure which way the material is coming in around the black hole due to the distance the material will get to the black hole. I'm going to come back to this point in a minute. It's important for helping to understand black holes and also define them. So because of the frame dragging, we get some kind of like complex structure around a rotating black hole. So we've got our singularity somewhere in the middle, and then we've got this radius here, which is the event horizon, and then we have what we call an ergosphere, which you can see here in the brown around here. This ergosphere actually touches the event horizon at the poles of the black hole, where the rotation is 0, and here, in the plane of the black hole, you can see that it's most extended and goes all the way out to the Schwarzschild solution. And it's in this region here where you have this problem with the frame dragging. So you get these particles that end up changing direction if they've got the wrong spin. So that's the theory. I'm going to do a tiny bit more theory in a few minutes, but that's most of the theory, and we're going to talk about observations. Because we want to know, are there black holes out there? Can we see black holes? Can we detect them? Can we find them somewhere? Most of the black holes that we found to date, stellar mass black holes that is, are in a system like you can see here. This is called a binary system. In the center here is a black hole, and this is a regular star. It could be a star like our sun, or it could be a star like the really big massive star that we saw before. So yeah, we're going to go back to our binary system. So there's 2 stars here. Right in the middle of this disk here is a black hole, and this is a regular star like the sun or the big blue star that I showed you earlier on, for instance. And because these 2 stars are very, very close together, and because the black hole has got this very strong gravitational field, it can pull matter off the star that's just nearby. So this is a binary system, and I need my hands to describe what I'm talking about, sorry. And so it's rotating like this, okay? So you've got the 2 stars going around each other, and their common center around their common center of mass. So this means that the material that's coming off here has also got some rotation, and it goes rotating around the black hole. And that's where it's going to lose its angular momentum, the speed it's got, inside this disk, by radiating light. And this is going to happen because the different particles are going to like rub against each other. And here the light's going to maybe not be quite so energetic, but right in the center the light's very energetic. And I'm going to come back to how we do that in a few minutes to try and detect it. So until recently, stellar mass black holes were all detected like this. You needed some matter that was going around your black hole to be able to find your black hole, because it's dark, black, you can't see it. So have we found any of these things? Yes. We found the first one back in the 1960s. This system is called SIG-X1, and it was very similar to the image that was on the page, the preceding page. So going back to the 1960s, we first started to discover these black holes, and you can see the number on the y-axis of black holes that we've discovered with time up until about 2015. And you can see we're sort of getting close to about 100 stellar mass black holes that we know of. The majority are in our own galaxy, and others are in nearby galaxies that we can detect. So how do we often detect these things? We usually use X-rays to try and find black holes. Why would we want to use X-rays, and what are X-rays? So this is the electromagnetic spectrum. You're probably familiar with this bit of the electromagnetic spectrum. This is the part you use with your eyes to see everything around you. So you recognize that you got the rainbow from the red to the blue. This is the lowest energy part of the visible light, and this is the highest energy part of the visible light. And that's important to understand. We'll come back to that too. So we've got the visible light that you know, and then there's all the other kinds of light you use, but not maybe in the same way as you do with your eyes. So we have radio emission, which you often use nowadays for the Wi-Fi. Infrared emission, you see this kind of emission being detected in spy films, for instance, with glasses that you can find people at night because they radiate thermal emission, which radiates in the infrared domain. Ultraviolet, I know, if you want to go out and sunbathe, you want to get a nice tan, UV is quite handy. The X-rays, you're probably more familiar with them when you go to the hospital and have to have an X-ray, if you've got a broken bone or something. And then gamma rays, which are the most energetic part of the electromagnetic spectrum. And you're probably most familiar with gamma rays with the residual from a nuclear bomb, for instance. So going from here to here, we've said we get more energetic. And the matter that's spinning around a black hole is very, very energetic. And in fact, it's seen most clearly in the X-ray domain, which is why we use X-rays to try and detect our black holes. And that's something that this observatory has been doing for the last 20 years. This is Newton. It's a European Space Agency mission that was sent up on the 10th of December 1999, so we're going to celebrate the 20th birthday next month. It's the most sensitive X-ray observatory we've ever sent into space, and it's capable of detecting a huge number of sources, and more than half of the sources it's detected have been black holes. So how can we be sure that the emission that we've got, that we've detected in X-rays, is really coming from a black hole? So we're going to go back to theory again, we're going to go back to relativity again, I'm afraid. And we can try and understand whether the emission we've got coming, that we've detected with our observatory XMM is from a black hole. And as we've said, around a black hole we've got very strong gravity, and this is where relativity is necessary to understand the nature of the emission. So often we can see emission coming from any object, and it will just be an emission with one single peak. It'll look a bit like a mountain, which is good. If we have an accretion disk, so if we go back to our image here, this accretion disk is much bigger than the size of the black hole. And in this accretion disk, some of the material is coming towards you, the material is coming towards you there, and that is the bit that's coloured in blue. And then some of the material is going away, so you've got the part that's moving away from you. And this is coloured in red, and that's known as redshift. You've probably heard of redshift before. Material that's moving away from you by the Doppler effect, so this is nothing complicated, it's nothing to do with relativity or Einstein or anything like that, is shifted to longer wavelengths. So you're quite familiar with the Doppler effect when you're standing on a busy street where the cars are like zipping past you, and the cars are going past and you hear the car going meow, meow as they go past, okay? This sound is just due to the Doppler effect. You hear a slightly higher sound, a little bit more, it's a higher sound that, as the car is coming towards you. As it goes away, the sound is lower. Okay, so you've got a lower frequency that moves away and a higher frequency as it's coming towards you. Okay, so this is the lower frequency, which is why we've coloured it red, and this is the higher frequency, and that's why we've coloured it blue. So our disk has got a bit coming towards us, which is blue shifted, and now blue is on this diagram. I'm sorry, it's switched around. Blue is this way, towards the right. So you see a peak in the blue, where the matter is coming towards you, and then you see another one in the red, where it's going away from you. So instead of seeing one single peak, we see two. Okay, so this is a really good sign of an accretion disk. But it doesn't tell me it's around a black hole. What tells me it's around a black hole is the three following images that we have. First of all, we're going to take into account the special relativity. And special relativity tells me when I've got matter coming towards me at almost the speed of light, the light from that matter is actually boosted. It's called Doppler boosting, which means that actually it's just magnified. So you might find the light, instead of being, I don't know, 5, it's 50. Okay? And the stuff moving away has got the opposite problem. Okay? It's less magnified. So here we'll see a really big peak because of the Doppler boosting of the matter coming towards us, and what's moving away here has got a smaller peak than we saw before. So that's special relativity. But then we need to also take into account general relativity because we're close to the black hole. And what we see is, this is not the actual physical description, but it can be understood in this way, that actually the light that's coming is inside its gravitational potential, and it's trying to get out, and it's using up all of its energy to try and get out of that potential, and it loses energy. And so we see a redshift, an extra redshift, because the light is losing energy, and so we see a shape that starts to become elongated towards this red wing. So if we take these three profiles and add them all up, we actually end up with a profile that looks like that. And if I detect this from an X-ray emitting object, I know that I've got emission coming from around a black hole. Only the black hole can cause this kind of profile. It's the only object that's got a strong enough gravitational field to do this. So we can go back to our three examples that we had before. Remember, we had the prograde spin, where we're going circulating in the same direction as the black hole. We've got the static black hole, the one that's not spinning at all, but the material is. And then we've got our retrograde black hole that's spinning in the opposite direction to the material. And in fact, the lines have changed for each one of these. So here, because we get very close to the black hole, we've lost a lot of energy here into the red wing, into this lower energy. And so we see a very flattened kind of profile. The line doesn't look quite as nice and tall as it was before. That's when we've got no spin, and when it's in the retrograde, it looks like this. So we can actually use that line to find a black hole, but then also to discover how fast it's spinning and in which way. So this is what we do to try and understand the nature of the black hole. So those are stellar mass black holes. Those are black holes that have been formed from the collapse of a regular star, a massive star. Are there other black holes? We talked about almost 100 stellar mass black holes that we know. Yes, we know today that massive galaxies contain black holes in their center. But these are not stellar mass black holes, these are what we call supermassive black holes. They are really massive. They weigh between 1 million and 10 billion times the mass of our sun. So they're much more massive than the stellar mass black holes that we were talking about. How can we be sure? Here you can see an image of taken with a Hubble Space Telescope. And you can see many, many galaxies here, and each one of these has got a supermassive black hole in the center. But how can we be sure about that? So this is a small film put together by the European Southern Observatories, and we're taking a trip into the center of our own galaxy, which is called the Milky Way. And as we get to the very center of our galaxy, these are the stars that are the closest to the central supermassive black hole. This is real data that's been taken using the Very Large Telescope in Chile. You can see the stars moving with time. So to help you guide your eye, they've drawn these orbits on there, so you can see blue lines, okay? The blue lines are not in the center of the galaxy, they've just been drawn on to help you understand. But the movement of the stars is real, and this has been measured since 1992. So we'll look at that just one more time. It should come back, I hope. And if it doesn't, try again. Okay, we'll go through it one more time so you know what you're going to look at. So we're going to travel through the gas and the dust to try and get to the center of our galaxy. And as we get there, we're going to come up against these stars that are traveling around some point-like, very massive thing in the middle of our galaxy. And you can see the path of these stars moving around this central point-like object. You can see it a little bit clearer in this one. There's only some of the stars, but we're right in the very center of the galaxy now. And actually the galactic center is at this point. You can see there's nothing there. There's no light or bright thing that's there. But all of the stars are going around that point. Every single one that you can see there. Some get very close, some get less close, but they're all going around this central point. And we could use laws that have been proposed by Kepler from studying the planetary system, so the different planets around the sun, to determine the mass of this central point. And this has been done very precisely because we've got so many stars. These are just a few of the stars. You saw some of the other ones in the previous video. And we've managed to determine that actually the mass of the black hole in our own galaxy, which we call Sagittarius A star, that's the name of the black hole, is actually 4.31 times 10 to the 6th solar masses. So it's pretty accurately determined thanks to these equations. So we said that supermassive black holes could be 1 million and up to 10 billion times the mass of the sun. So you can see also that our black hole in the center of our galaxy is actually very small. It's only at the very bottom end of these supermassive black holes. It's difficult to do this kind of work exactly for other galaxies. It's very difficult to actually see the individual stars. This is exceptional. These are pretty close, these stars, to us. Other galaxies are a really long way away. So we can't find individual stars, but we can actually see the motion in general of the stars going around the black hole, and also the gas that's going around the black hole. So we can do this kind of work again for a lot of different black holes in different galaxies. And that's what is represented on this plot. So on the y-axis here, you've got the masses of black holes that have been measured in different galaxies. These are supermassive black holes. And you can see the different masses here. And they've been plotted as a function of the luminosity of the galaxy. Why did we take the luminosity of the galaxy? Well, the luminosity is correlated with the number of stars. More luminosity, more stars, more mass. So as we go along here, we have higher mass galaxies that have got many, many stars. And as we go up here, we've got the higher mass black holes, going up to this 10 to the 10th solar masses, which I said, 10 billion solar masses. And you can see there is actually a correlation between these two values. There seems to be some kind of correlation between the mass of the galaxy and the mass of the black hole. Why that should exist, we don't know yet. It's something we're working on. We're trying to understand why a black hole, which is so small that it only influences the very, very central part of a very, very big galaxy, why should that black hole have such an impact on the mass of the galaxy? How does the galaxy know the mass of that black hole and then to build itself up till it gets to the right mass? So it's something we're working on actively. But there's many other questions about black holes too. We've talked about some of the masses of black holes. We've talked about black holes of 10 billion or million solar masses, the supermassive black holes. And we've talked about stellar mass black holes, which I've said maybe 10 or 20 times the mass of our sun. But are there other kinds of black holes? Also, where do they form? I said that stellar mass black holes can form from a star. When did that happen? Did that happen at the beginning of the universe? Is it happening today? We'd like to know. How many are there? We've got a population, I showed you nearly 100 stellar mass black holes, and we've got millions of supermassive black holes, but how many are there really? Because we're only looking at a very small part of the universe. And one of the other questions, a very big question that's open today, is how do the supermassive black holes form? The stellar mass black holes, we've understood they form from a massive star, but you can't make a massive star of 10 billion solar masses that can explode and finish its life as a 10 billion solar mass black hole. So it's been proposed that these supermassive black holes are maybe built up from some other black holes. Imagine if we made a 10 solar mass black hole right at the beginning of the universe, and then lots of matter fell onto a black hole through accretion, through this disk, taking matter from other stars. It might even find other black holes and merge to create a bigger black hole. Even if we did that right from the beginning of the universe and put as much matter onto that black hole as possible, we would not be able to reach the 10 to the 10 solar mass black holes that we see today. It's not possible. So these black holes must have formed in some other way, not from the end of the life of the star. It must have been something else. And it's proposed that maybe they get formed from intermediate mass black holes. So these are black holes that have got masses between 100 and 100,000 solar masses that could have realistically be formed right at the beginning of the universe. So that sounds good. We've got a theory, so we need to prove it. But how do we prove this theory? Well, we need to find some intermediate mass black holes that are left over from this process. We expect some of them to be left over, but they're difficult to find. One way you can try and go about finding these things is to look for a very exceptional event, which is called a tidal disruption event. So what happens here is you've got your black hole that's here, and some of the star in your galaxy, and it gets knocked off its orbit for some reason, and it starts to fall towards the black hole. When it gets close to the black hole, it gets compressed and eventually completely destroyed, so that all of the matter from half of the matter from this star will fall onto that black hole, and we'll suddenly see it get extremely bright. This happens preferentially around the lower massive black holes, and it's one way to try and find these intermediate mass black holes that we've been looking for. They're also quite easy to identify, because this becomes bright very suddenly. All of a sudden it gets very bright, and then it drops off, the light. And that's what we're seeing here. So this is the amount of X-ray light that we're seeing, and this is the time. And this is one example of one we found. We don't know when it got bright, because we didn't see the beginning, but we did manage to track it afterwards. And these are some of the data points that we've taken in X-rays to try and see how it's evolved with time. This line is not a fit to that data. This line is a prediction of what that data should do. And as you can see, the data actually fit it very well to describe one of these disruptions of a star that happened. And in fact, the one we found here has actually got a mass that appears to imply that it's an intermediate mass black hole. We also found another object back in 2008, which is this object that looks very insignificant here, but in X-rays can be very, very bright. And this is currently the best intermediate mass black hole candidate that's been discovered. There's been a huge amount of work on this object, because in fact, instead of just going bright and then fading, it then does it again, and then it fades, and it does it again and fades. So we've had many, many times we've been able to observe this star. And we think that this brightening happens because actually the star doesn't get completely destroyed, and it keeps going around in a binary system, almost getting destroyed by the black hole, but not quite. And then so material is dropped onto your black hole, and then it gets faint again until the star comes back, and then it gets bright, and then it fades again. So that's where you can detect black holes, and in fact that's what we did until 2015. And then everything changed for the better, which is good. So another prediction of general relativity is what we call gravitational waves. So we talked about the space-time, these 4 dimensions, and we saw how the black hole deforms the space-time. But if we have 2 black holes orbiting each other, this is going to cause little tiny ripples in the space-time. So when you throw a stone into a lake, for instance, you see these little tiny ripples that come off the the area where you threw the stone in. And these are almost the same. So you get these tiny ripples in the space-time. This is predicted by general relativity, and people have been searching for this emission for 60 years, because this would be ideal if we can detect this kind of emission, because we don't need light, we don't need any of the electromagnetic spectrum, we don't need to have XMM up in space looking for this. We can detect just these little ripples in space-time. So they look a little bit like this. This is just artist impression. But yeah, you can see the two black holes orbiting each other, and this is the kind of little ripples that you see in space-time. They are so small that they're very difficult to detect, which is why it's taken 60 years to do so. But we managed in 2015, and it was this facility, which is called LIGO, which is situated in two different places in the United States, one in Livingston and one in Hanford, that is capable of detecting these tiny little ripples. It's very difficult to do, so they've got these very long tunnels here that are 3 kilometers in length. There's one here and one there, and you see the same thing here as well, the other one. And actually the signal has to be multiplied several times inside that tunnel before you're able to detect it. And it's very difficult to find these things. Even a truck going past at 10 kilometers away actually can cause a false detection in these kind of detectors. But they did manage to detect 2 black holes that were orbiting each other and eventually coalesced to make one big black hole. And that was back in September 2015. And here are some of the results. These are only the very first results that have been taken with these gravitational wave observatories, but it's revolutionizing our understanding of black holes. Why? First of all, as I say, we don't need to have light coming from our black holes, so we can detect black holes that are paired up together and not with some other star. But also, what you see on this plot is the mass of the black hole here. And in purple are the black holes that we know of, the ones that we knew of before the gravitational wave detections. And you can see the maximum masses that we've got here are actually quite low. They're sort of around 20 times the mass of our sun, 20 solar masses, which is the kind of mass I was giving you. And what you can see here is the ones that have been detected by these gravitational wave detectors are actually significantly larger. And in fact, we've been detecting more and more of these objects, and they reach up to 50 times the mass of our sun, which previously theoreticians said, not possible, can't form a stellar mass black hole as massive as this, as 50. But obviously it must exist, we're detecting them now. So 2 of them will coalesced to form a black hole of 80 solar masses. So we need to try and understand why they're so massive, how they managed to get so massive, and also, how come we're finding so many of these black hole coalescences when we thought that they would actually be other kinds of objects like neutron stars. So neutron stars are not quite the finals, it's not as dense as a black hole. These have got a solid surface, and we expected to find the coalescence of many of these kinds of objects. So you can see the neutron stars that we know in yellow here, and we have actually detected the coalescence of 2. We don't know what it formed. We don't know whether it formed some other neutron star or some black hole. But we expected to find many more of these and many less of these, and it's the wrong way around. So there's something we don't understand about stellar evolution. We're trying to understand now. So just one final thing. We've talked about these radii, but we've not really said how big they are. So stellar mass black holes, if we think of one of about 3 solar masses, that's how big it is. So it weighs 3 times the mass of our sun, but it's actually about the size of Toulouse. Okay? So these are very, very small. And the size I've given you here is the event horizon. Okay? So it's probably some singularity in the middle, but this is the event horizon of our black hole. What about the other ones, the more massive ones? So for a 10 to the 6 solar mass black hole, the one like Sagittarius A star, so 1 million solar masses, is a bit bigger than our sun. Okay? And if we had a really massive one, like 1 million solar masses, it would come all the way out to the end of Saturn, approximately. Okay? This is just the event horizon. Obviously, as I say, it could be a singularity on the inside. But these are very small objects, so you can understand why it's puzzling how these can have such a big influence on the whole of the galaxy.